Welcome to chapter 26d, relativity, length, and time and velocity. We're going to be talking about relative velocities, time dilation, and length contraction. The first topic of the day is time dilation. Now, the figure here shows a special clock called a light clock. The light clock is a box with a light source at the bottom, a mirror at the top. This light source and the mirror are separated by distance h, and there's also a light detector next to the light source. The light source will emit a very short pulse of light that travels to the mirror and reflects back to a light detector beside the source, and the total distance is 2h. The clock will advance one tick each time the detector receives a light pulse. A light travel time is the time for the tick, and in the clock's reference frame, it is equal to 2h over c, where c is the speed of light. The clock is at rest in frame S prime. So frame S prime is the rest frame of the clock. Of course, reference frame S prime is moving to the right with velocity v in the x prime direction relative to reference frame S. Now, the figure shows the light clock as seen in frame S. Clock, of course, is moving relative to frame S. So here is the clock in the mirror when the light was emitted. Here is the mirror and the clock when the light gets bounced off the mirror. And here is the mirror and the clock when the light is detected. Now, with each tick, the clock will move a distance v delta t relative to frame S, and the light will travel a path that is greater than the 2h it covers relative to its own reference frame. As viewed from frame S, the clock must tick more slowly since light must travel along a longer hypotenuse at the constant speed c. Remember, the speed of light does not change. So in frame S, the light will take a time delta t to travel along the hypotenuse from the emitter to the mirror. And we can use this Pythagorean theorem, apply it to this triangle, to write a squared plus the square of the quantity 1/2 v delta t equals the square of the quantity 1/2 c delta t. We solve this for delta t. Delta t will then be 2h over c divided by the square root of the quantity 1 minus v squared over c squared. And we can say that delta t prime is 2h over c. We're going to define that as delta t prime. So then delta t equals delta t prime divided by the square root of the quantity 1 minus v squared over c squared. Now you're going to see this square root of 1 minus v squared over c squared everywhere. So we're going to do, and we'll also see v over c everywhere too. So we're going to define the dimensionless number beta equals v over c. We're also going to set gamma equal to 1 divided by the square root of the quantity 1 minus beta squared. Now, gamma is always greater than or equal to 1. Delta t equals delta t prime divided by the square root of the quantity 1 minus beta squared, or gamma delta t prime. So the time interval between two events that occur at the same position is called the proper time delta tau. The proper time is measured with a single clock that is present at the same place relative to its reference frame for both events. An inertial reference frame moving with velocity v equals beta c relative to the proper time frame must use two clocks to measure the same time interval, one at position of the first event, the other at position of the second event. The time interval between the two events in this frame is delta t equals delta tau divided by the square root of the quantity 1 minus beta squared. That's always greater than or equal to delta tau. This is time dilation. Moving clocks run slow. So measurements of the same time interval in other reference frames are always greater than the proper time interval. Now we've tested this many ways. One of these ways is with unstable particles called muons. These are created at the top of the atmosphere when high-energy cosmic rays collide with the air molecules. These particles decay with a half-life of 1.5 microseconds in their own reference frame, but they're moving at a relativistic speed much greater than 99% of the speed of light relative to our reference frame. So their clocks, the life clocks of the moving muons, run slow relative to our clocks, so they last much longer. 1.5 microseconds, a muon would probably only travel, even at this high speed, about 450 meters. The top of the atmosphere is 100 kilometers up, at least. Because of time dilation, the half-life of the muon is long enough in the Earth's reference frame for about 10% of them to reach the ground, so we actually detect them. That's one of the tests of time dilation. Now, the global positioning system allows you to pinpoint your location anywhere in the world to within a few meters. It uses a set of orbiting satellites, and it depends on the timing of atomic clocks. Because of the motion, the atomic clocks on these satellites keep time differently from the clocks on the ground. To determine an accurate position, the software in your GPS receiver must carefully correct for time dilation effects. On top of that, they're in a gravity field. So we also have to correct for gravity's effect on space-time, and that's general relativity. So GPS wouldn't work without special and general relativity. Now we're going to come to something that's extremely famous in relativity called the twin paradox. So we have George and Helen, who are twins. On their 25th birthday, Helen departs on a starship voyage to a distant star. Helen's starship travels at the speed of 95% of the speed of light to a star that is 9.5 light years from Earth. So in terms of Earth years, it's going to take her 10 years to get to the star. Upon arriving, she immediately turns around and heads back home at 95% of the speed of light. So it's going to take her another 10 years to come back. According to George, it takes Helen 20 years to travel out and back. Now, this is according to George. That's Earth time. George will then be 45 years old when his sister Helen returns. In George's reference frames, Helen's moving clock will run more slowly than his stationary clock. Helen's clock travels with her, so it measures all events from the same location in her reference frame, uses a single clock, so it measures the proper time, delta tau. Delta t for Helen is delta tau. That's the proper time. That equals delta t for George, that's Earth time, times the square root of the quantity 1 minus beta squared. So we take our 20 years, take the square root of the quantity 1 minus 0.95 squared, and we wind up with 6.25 years. So Helen will only be 31.25 years old. She's about 14 years younger than her twin brother. George will be 45 years old. Now this is where the paradox comes in. George is standing on the Earth. He watches Helen go by. Helen is moving relative to me at 0.95 C. Her clocks are running more slowly than mine, and when she returns, she'll be younger than I am. Helen on the rocket ship says, George is moving relative to me at 0.95 C. His clocks are running more slowly than mine, and when I return, he'll be younger than I am. This is the paradox. Who is correct? Well, it turns out it's George. Helen forgot a very crucial fact that this only applies to inertial reference frame. So even if she goes out there and turns around and comes back, goes out at constant speed, 95% of the speed of light, turns around at 95% of the speed of light and comes back at 95% of the speed of light, she turns around. She changes direction. That's an acceleration. She was making a calculation that only applies to inertial, non-accelerating reference frame. So our equations for time dilation are only valid for inertial reference frames. George's analysis and calculations are correct since his frame is not accelerating. He will be the older twin at journey's end. Helen's analysis and calculations are not correct because she was trying to apply an inertial reference frame result while traveling in a non-inertial reference frame. In other words, the minute you accelerate, all bets are off. Helen is younger than George when she returns. Most women I know would be very happy with this. So also Helen would see 20 years pass in George's reference frame. George would see only 6.25 years pass in Helen's reference frame because her clock runs slow. Now we're going to talk about length contraction. So we're going to consider a rocket which travels from the sun to Saturn at speed v. In the reference frame of the solar system, the distance traveled is L, and v equals L divided by delta t, where delta t is the time for the rocket to make the journey in the S frame. That's the frame of the solar system. Okay, in the reference frame S prime, which is the rocket's rest frame, the rocket is at rest and the solar system moves to the left at speed v. The relative speed between S and S prime is the same for both reference frame. So v equals L over delta t. It also equals L prime over delta t prime. Delta t prime is equal to the time it takes for the trip in the S prime frame. That's measured by the rocket's clock. The time interval delta t prime measured in frame S prime is the proper time, delta tau, because both events occur at the same position, that's the rocket's clock, and frame S prime, and can be measured by one clock. So delta tau equals delta t times the square root of the quantity 1 minus beta squared. Since the speed is the same in both frames, L over delta t equals L prime over delta tau, and that equals L prime over delta t times the square root of the quantity 1 minus beta squared. The delta t will cancel from this, and we can solve for L prime in frame S prime. L prime will be little l times the square root of the quantity 1 minus beta squared, where little l is the proper length measured in the rest frame of the object. The length of any object is less when it's measured in a reference frame in which the object is moving. Moving objects shrink, but only in the direction in which they're moving. Now, here's an extreme example of length contraction. This is the Stanford Linear Accelerator. It is a 2-mile-long electron accelerator. The proper length is L equals 3,200 meters. The machine accelerates electrons to more than 99% of the speed of light. The accelerator's length is less than 1 meter in the moving reference frame of the speeding electron, so L prime is less than 1 meter. And that's a real example of length contraction. Now here's another example. Remember those muons that are created at the top of the atmosphere when high energy particles collide with air molecules? These particles decay with a half-life of 1.5 microseconds in their own reference frame and are moving at relativistic speeds, greater than 99% of the speed of light relative to our reference frame. This means that the distance they travel in their reference frame is shrunk by length contraction. So to them, instead of having traveled 100 kilometers to the ground, they don't have to travel as far. So they live long enough to reach the ground before they decay. So we're going to take an example here. We're going to take a trip to Saturn. A rocket travels along a line from the Sun to the Saturn at a constant speed of 0.9 c relative to the solar system. The Saturn to Sun distance is 1.43 times 10 to the 12 meters. What is the distance between the Sun and Saturn in the rocket's reference frame? The physics of this is length contraction at relativistic speeds. The knowns and unknowns. Little l is 1.43 times 10 to the 12 meters. B is 0.9 c, and L prime we don't know. The formula is L prime equals little l times the square root of the quantity 1 minus beta squared. We plug in our little l of 1.43 times 10 to the 12 meters, and we take the square root of the quantity 1 minus 0.9 squared. We find out that L prime is 0.62 times 10 to the 12 meters. So this is less than half the distance in the solar system's reference frame. So space has been altered and shrunk. Now here possibly is another paradox. Students ask me this all the time. We have Carmen and Dan, each carry meter sticks and run past each other in opposite directions at a relative speed of 0.9 c. Carmen looks at Dan as he runs by and says, Dan's meter stick is shorter than mine. Its length is contracted because Dan is moving relative to me. Dan looks at Carmen and says, that can't be. Your meter stick is the one whose length is contracted. Your meter stick is the shorter one. Who's right? Because Dan's meter stick can't be both longer and shorter than Carmen's meter stick, and Carmen's meter stick can't be both longer and shorter than Dan's meter stick. Well, relativity allows us to compare the same events as they're measured in two different reference frames. But the events by which Dan measures the length of Carmen's meter stick are not the same events as those by which Carmen measures the length of Dan's meter stick. In Dan's reference frame, Carmen's meter stick has been length contracted and is less than 1 meter in length. In Carmen's reference frame, Dan's meter stick has been length contracted and is less than 1 meter in length. There is no conflict between their measurements. They would each see the other stick as contracted because of relative motion between their moving frames. They would also each see the other's clock as running slow. Length contraction versus time dilation. Remember, speed is distance divided by time, and the speed of light has to be the same in all inertial reference frame. So if the speed of light has to be the same, the ratio distance divided by time must be constant. So if a moving clock slows down, that is, less time passes for the moving clock, then length, that's the distance and direction motion, must also contract by the same factor. That factor is the square root of the quantity 1 minus beta squared. Only the length and the direction of motion is affected. Also, the speed of light as measured by a moving observer is not affected, but the wavelength, which is length related, and the frequency, which is time related, are affected. They are Doppler shifted by the relative motion between the light source and the observer. So now we're going to talk about the space-time interval. Consider two events that are separated in time by an interval, delta t, and are separated in space by an interval, delta x. Let us define the space-time interval s between the two events to be s squared equals c squared delta t squared minus delta x squared. Now, the space-time interval has the same value in all inertial reference frames. That is, the space-time interval between two events is an invariant that allows us to connect the two events. So here we're going to use the space-time interval. A firecracker explodes at the origin of an inertial reference frame. Then 2 microseconds later, a second firecracker explodes 300 meters away. Astronauts in a passing rocket measure the distance between the explosions to be 200 meters. According to the astronauts, how much time elapses between the two explosions? The physics of this is relativity, space-time interval. We're going to let the reference frame of the ground be s and that of the rocket be s prime. The space-time interval is the same in both reference frames. Now, knowns and unknowns. Delta t is 2 microseconds, delta x is 300 meters, delta x prime is 200 meters. We need to know delta t prime. The formula is s squared equals c squared delta t squared minus delta x squared. The space-time interval is an invariant. That means it's the same for both the unprimed and the primed intervals, so we can equate them. So we're going to say s squared equals c squared times delta t squared minus delta x squared. That has to equal c squared delta t prime squared minus delta x prime squared. And we can use this to get a relationship between delta t, delta x, delta t prime, and delta x prime. Okay, so we're going to solve it for delta t prime. Delta t prime will equal the square root of the quantity delta t squared plus delta x prime squared minus delta x squared over c squared. Now we can plug the numbers in. So we have delta t equals 2 microseconds. Delta x prime is 200 meters. Delta x is 300 meters. And we're going to write c in terms of meters per microsecond. So it's 300 meters per microsecond. When you do the calculation, you end up with 1.85 microseconds. The events are closer together in space and time in the rocket's reference frame than the ground's reference frame. Space and time are altered between moving frames. Now we're going to talk about the Lorentz transformation. The space-time coordinates of an event are measured in inertial reference frames S and S prime. We wish to transform the x, y, and z of the S frame to the x prime, y prime, z prime, t prime of the S prime frame and vice versa. Remember, the frame S prime moves at speed v relative to S. So the motion is parallel to the x and x prime axis. We define t equals 0 and t prime equals 0 as the instant when the origins of S and S prime coincide. The Lorentz transformation, or x prime, equals gamma times the quantity x minus vt, y prime equals y, and z prime equals z, because those coordinate axes are not affected by this motion. T prime equals gamma times the quantity t minus vx divided by c squared. Going the other way, we can say that x equals gamma times the quantity x prime plus bt, and again, y equals y prime and z equals z prime. T equals gamma times the quantity t prime plus vx prime divided by c squared. And of course, gamma equals 1 over the square root of the quantity 1 minus beta squared as before. Problem-solving strategy in relativity is pretty much the problem-solving strategy I've been talking about all along. You want to read everything, write everything, and think. So read everything, write everything down. Don't forget the units. Frame the problem in terms of events, things that happen at a specific place and time. Visualize, pick reference frames, and identify. Sketch the reference frames, showing the motion relative to each other. Show events. Identify objects moving with respect to the reference frames. Identify any proper time intervals measured by one clock at the same time and proper lengths measured in an object's rest frame. Pick appropriate formulas and solve. We'll use the Lorentz transformations, but not every problem requires the full transformation equations. Time intervals can often be solved using time dilation. Delta t equals gamma delta tau. Distances can be solved using length contraction. L equals little l divided by gamma. You always want to check your results. Does the answer make sense? Are the results consistent with Galilean relativity when v is much less than c? And are the units consistent? The figure shows an object of proper length little l moving along the x prime direction at speed v relative to frame S. Now, the object is at rest in frame S prime. Its length is L prime equals little l, which can be measured at any time. Because the object is moving relative to frame S, however, simultaneous measurements of its ends must be made to find its length L in frame S. So the Lorentz transformations for the positions of the right and left ends of this object are x prime r equals gamma times the quantity xr minus vt, and xl prime equals gamma times the quantity xl minus vt. In order to find the length L in S, we need to subtract these two quantities, xr prime and xl prime. So the length in S is L equals little l times the square root of the quantity 1 minus beta squared. The other dimensions, of course, are not affected because there's no motion in those dimensions. Peggy passes Ryan at velocity v. Peggy and Ryan both measure the time it takes the railroad car from one end to the other to pass Ryan. The time interval Peggy measures is longer than, the same as, or shorter than the time interval Ryan measures. Well, Ryan measures the proper time because both events for him occur at the same position in his frame. He only needs one clock to do this. He sees her clock running slow. She sees his clock running slow. But time intervals measured at any other reference frame are longer than the proper time interval. The time interval Peggy measures is longer than the time interval Ryan measures. Peggy passes Ryan at velocity v. Peggy and Ryan both measure the length of the railroad car from one end to the other. The length Peggy measures is longer than, the same as, or shorter than the length Ryan measures. Peggy measures the proper length because the railroad car is at rest in her frame. She only needs one thing to measure it with. So hers is the longest measured length. Due to length contraction, lengths measured in any other reference frame are shorter than the proper length. So the correct answer to this one is Peggy measures the longer length. Now, if you've had calculus, and please don't worry about this, because if you haven't, it doesn't really make any difference. And if you don't remember this, I'm going to show it to you now. If you've had calculus, you may have learned the binomial approximation. If x is much less than 1, then the quantity 1 plus x to the nth power is approximately equal to 1 plus nx. The binomial approximation is useful when we need to calculate an approximate relativistic expression for a non-relativistic velocity. So v is much less than c. So if v is much less than c, we want to take the square root of the quantity 1 minus beta squared and get an approximation for that. When we do that, we find that it is 1 minus 0.5 beta squared. We also want to do this to gamma. Gamma, of course, is 1 divided by the square root of the quantity 1 minus beta squared. When we do that, we find that gamma is approximately equal to 1 plus 0.5 beta squared. These make it easier and possible to calculate with a hand calculator when v is much less than c, because calculators don't carry enough digit. But be very careful with these. Use these only when v is much less than c. If in doubt, use the exact expression, not the approximations. Excel spreadsheets carry 32 digits, and Excel is free to everyone at WCC. Here's an example of the shrinking school bus. An 8-meter-long school bus drives past you at 30 meters per second. By how much is its length contracted as you see it? The physics of this is relativity, length contraction. V is much less than c, so we're going to use the low-speed approximation. Okay, the knowns and unknowns. We know the proper length, little l, is 8 meters. V is 30 meters per second. We're interested in the shrinkage, which is little l minus l. The formula for L is L equals little l times the square root of the quantity 1 minus beta squared. We're going to use the low speed approximation for that, so L is going to be approximately equal to little l minus little l over 2 times v squared over c squared. We're interested in the shrinkage, which is the difference between little l and L. And that equals little l over 2 times v squared over c squared. At this point, we can plug numbers in. Little l is 8 meters. We're going to divide that by 2. V is 30 meters per second. We're going to square it. And of course, c is 3 times 10 to the 8th meters per second. We're going to square that. When we crank the numbers, we wind up that the difference, the shrinkage, is 4 times 10 to the minus 14th meters. Now, this is only slightly greater than the size of an atom. It would not be possible to use a hand calculator and the exact expression to calculate this, because this is 0 to 14 places, and the calculator does not carry that many digits. You could do it easily with an Excel spreadsheet. If I remember correctly, Excel carries 32 digits. We want to come up with the Lorentz velocity transformations. We have two frames. Frame S prime is moving at velocity v with respect to frame S. Frame S is moving at a velocity minus v with respect to frame S prime. Experimenters in frame S determine that an object's velocity relative to that frame is u. Experimenters in frame S prime find the same object's velocity relative to the S prime frame is u prime. For simplicity, we'll assume that the object moves parallel to the xx prime axis. For other axis, you just substitute appropriately, or you can always turn the coordinate axis around. We want to find a way to transform velocity from one frame to another. So remember, the frame S prime is moving at speed v relative to S. An object has velocity u and s, and u prime and s prime. It's the same object. All motion is parallel to the x and x prime axis. The Lorentz velocity transformations are u prime equals u minus v divided by the quantity 1 minus uv divided by c squared. And u equals u prime plus v divided by the quantity 1 plus u prime v divided by c squared. Be very careful of the signs on relative velocities. So Sam flies past the Earth at 75% of the speed of light. That's 0.75 c. As he goes by, he fires a bullet in the forward direction. That's the same direction as he's traveling, as his rocket's traveling, also at 0.75 c relative to the rocket. Susie on the Earth measures the bullet speed to be, now, it can't go faster than the speed of light. So anything that says 1.5 c is not going to be correct. They're going in the same direction. So it can't be less than 0.75 c. It can't be 0.75 c. It can't be c. So it has to be between 0.75 c and c. Speeds do not exceed c. So you can't just add that up, because this is special relativity, not Galilean relativity. Now here's a very fast bullet. A rocket flies past the Earth at 0.9 c. As it goes by, the rocket fires a bullet in the forward direction at 0.95 c with respect to the rocket. What is the bullet speed with respect to the Earth? The physics of this is relativistic speeds. We're going to use the Lorentz velocity transformation. We're going to set the reference frame equal to Earth. We expect that the answer will be close to but less than C. Positive direction is set in the forward direction of the rocket. That's away from the Earth. So we know the knowns and unknowns. The V is 0.9C. The U prime is 0.95C. What is U? The formula is U equals U prime plus V divided by the quantity 1 plus U prime V divided by C squared. Now we can plug our numbers in, 0.95C for U prime, 0.9C for V, and ditto for down here, 0.95C for U prime, 0.9C for V. And when we do that, we find out that U equals 0.997C. U is less than C, as expected, but it's almost the speed of light as expected. Now, if you had not used the proper physics, you might have found that U equals 1.85C, which is obviously not correct because you can't travel faster than the speed of light. Now, here's almost the same example. We're going to fire the bullet in the opposite direction. So a rocket flies past the Earth at 0.90C. As it goes by, the rocket fires a bullet in the backwards direction at 0.95C with respect to the rocket. What is the bullet speed with respect to the Earth? The physics of this is still relativistic speeds. We're going to use the Lorentz velocity transformation. The reference frame is still set to Earth. We expect that the answer will be considerably less than C. The positive direction is in the forward direction. That's away from the Earth in the same direction as the rocket. So now we know that V equals 0.9C as before, but U prime is now minus 0.95C. Again, note the sign, and we need to know U. So we can still use the same formula we had before, U prime plus V divided by the quantity 1 plus U prime V divided by C squared equals U. We plug in our numbers, but now U prime is negative 0.95C and V is still 0.9C. And when we do the calculations, we find that U is negative 0.345C, and that is less than what it was than C, which is good. It's in the negative direction, which is also good. Thank you.